Hi everyone, this is lesson 2.3.1 in our transformations chapter, and this is the lesson on reflections. Now, most reflections that we're going to work with are going to require the introduction of a negative in order to get a reflection over one of the axes. And we know that negatives can cause a lot of confusion, so I just want to remind you to be really careful when you're applying the rules regarding negatives. And another place where extra care needs to be taken will be when working with inverses. You're going to be asked to restrict the domain of the original function in order to make sure that the inverse is also a function. And in many cases, that can be a really complicated thing to do. Now let's take a look at our first example. Given f of x is equal to x minus 4 squared plus 3, write the equation of the following transformations and sketch them below. Using interval notation, identify the domain and range of the resulting functions. Okay, so the first one we're going to look at here is y is equal to negative f of x. Now, since the negative is in front of the function, we know that it's going to be distributed to both terms in the function. Additionally, we also know that this means that this is going to be a vertical reflection because it is the the dependent variable that's changing signs here. And now, just like we've done a number of times before, it really is going to help us to see the original graph before we sketch the transformation. So here's a look at the graph of y equals x minus 4 squared plus 3. It's just a parabola with a vertex at the point 4 comma 3, and it opens up. Now, when we distribute the negative through, we're going to get that y is equal to negative x minus 4 squared minus 3. And you can see what that does. It's now a parabola that opens down with a vertex at the point 4 comma negative 3. The domain is going to stay the same. It's going to be infinite, all reals, negative infinity to positive infinity. But in this case here, the range is going to be a little different. And actually, my notation is slightly incorrect here. It should go from negative infinity up to negative 3 and including negative 3. There should be square brackets around that. Now let's take a look at the same question with a slightly different reflection. Now we're going to look at y equals f of negative x. Now in this case, the negative is within the function, so only the terms with the independent variable are going to change signs, or the x. And that means that this is going to be a horizontal reflection over the y-axis. So if something's to the right of the y-axis, it's going to flip to the other side. This does, however, make things just a little bit more complicated. So let's take a quick look at the function here. So f of negative x is going to be equal to negative x minus 4. And I apologize for this because I know what I did, but it's screwed up here. But it should be negative x minus 4 squared plus 3. Now, in order to clearly see the transformations in this function, what we need to do is factor that negative away from the x. So that's going to leave the horizontal translation much clearer to us. So I have to take the negative out of the x and the negative 4 there, but not quite out of the square yet. So I get parentheses, negative, parentheses, x plus 4, close bracket, that is all squared, plus 3. And when we apply the square now to both of the factors within it, the negative is going to go away, and so we're just going to be left with x plus 4 squared plus 3. Now, once again, it helps a little bit to look at the graph. And here's the graph of x minus 4 squared plus 3. Again, it's just a parabola that opens up with a vertex at the point 4 comma 3. And then we know that the horizontal reflection is going to give us this function x plus 4 squared plus 3. And you can see that it's been flipped over the y-axis. The domain has not been affected, and a horizontal reflection wouldn't anyway. It's all reals, negative infinity to infinity. And the range has not been affected either. This is not a vertical transformation, it's just a horizontal one. So in this case, we start at 3 and go up to infinity. Now let's take a look at a fairly easy question that is often misread. If f of x is equal to 10x minus 1, then g of x is equal to negative 10x minus 1 is going to be a reflection over what? Now, what you got to notice here is that only one term changed signs. It was the first term. But that is sometimes confusing for some people because that negative is up front. And because that negative is up front, people want to think of this as a vertical reflection. But had this been a vertical reflection, the negative would have been distributed through all of the terms of the function. And because that isn't true in this question, it must be the case that this is a horizontal reflection over the y-axis. Now let's look at the next question. The graph of y equals f of x, where f of x is the absolute value of x plus 6 minus 1, is reflected in the y-axis. We can get the same result by translating the graph of y equals f of x to the right by how many units? In this case, to find the solution of the problem, it helps to consider the transformations required to create the original function that we're working with. And we see that the function f of x represents an absolute value function that has been translated 6 units to the left and 1 unit down. Now, reflecting this over the y-axis would result in a graph that had actually been translated 6 units to the right. And with just a moment's consideration here, I think it'll be pretty clear that to go from 6 to the left to 6 to the right we can achieve that same result by simply translating that graph 12 units to the right. Now we're going to take a step back and just take a quick look at what happens to individual points when we do these reflections. So given the point -5, 2 is on the graph of the function y equals f of x, state the coordinates of the corresponding point on, and in our first case here it's going to be y equals f of -x. Now to answer this question, it's really important that you see that this is a reflection over the y-axis. And as such, we know that the image point will be x comma y will map to -x comma y. When we apply this to the given point, we get the image point to be 5, 2. The next question asks us to find the corresponding point on the graph of y equals -f of x. And once again, we need to know what direction this is, and this is a reflection over the x-axis. And the image point in this case will be going from x comma y to x comma -y. And when we apply this to our original point, we get an image point of -5, -2. Now, you wouldn't often expect them to do this, particularly on the diploma exam, but we're just going to take a quick look at what happens if you put both of those reflections together. Well, this is quite clearly a reflection over both axes. And so our mapping point will be -x, -y. When we apply this to our image point, we get a final point of +5, -2. Okay, now let's take a look at a question that's asked in a slightly different way here from the previous questions. In this particular case here, we're going to rely on the graph to give us the information about the reflection. So in this case here, the thin line represents a transformation of the function represented by the thick line. So write the equation of the thin line given that the function of the thick line is, and in this case, the first case here, it's going to be y equals x plus 1 over x minus 4. Now in this case, given the chapter that we're in, we need to assume that the only transformations that have taken place are reflections. Okay, this is a pretty safe assumption because of what we're trying to cover at this point. Now, when a graph and its inverse are plotted on the same grid, they could intersect at multiple points here. But the graph and its inverse will always intersect at the invariant point. Now notice in this case that the invariant point is going to be on the y-axis. Now, granted, it looks like it might also be on the x-axis as well, but the shape of the resulting graph seems consistent with just a single reflection. So with the invariant point on the y-axis, we know that this is a horizontal reflection. So now we're going to replace x with -x in the equation of the function, and then we get y equals -x plus 1 over -x minus 4, which we would then proceed to simplify by factoring out a -1 out of the numerator and the denominator. Now, I've written it in the numerator just to be clear, but you don't need to write the 1. You can write it as I did in the denominator with just the negative outside. And then we can cancel the negatives to get x minus 1 divided by x plus 4. Okay, in this next question, notice that we're still looking at the same function, but the reflection is different. And just to reiterate, we're assuming that it's only been that the only transformations that have occurred have been reflections. Now in this case, notice that the invariant point appears to be on the x-axis, and that this means that there's been a reflection over the x-axis. So because of that, we know that there's been a vertical reflection, and thus we're replacing y with -y in the equation of the function to get -y equals x plus 1 over x minus 4. And then all we really need to do to simplify this is to bring the negative from one side over to the other. So now we get the function -x plus 1 divided by x minus 4.